welcome to another module in this massive open online course. So, we are looking at delta modulation, and we have said that delta modulation is an efficient scheme for quantization, because rather than quantizing the signal samples, it quantizes the differences. And further, very interestingly, the differences are represented only using a single information bit. So, it is very efficient, alright. It quantizes the signal, and as we said, it can also be used for compression of the original signal. That is, instead of using a large number of bits per sample, only a single bit can be used to represent each sample, and very efficiently. Okay. So, let us note this. So, we are looking at delta modulation. Which is really a scheme for differential modulation, because it encodes the differences, correct. It is a differential modulation scheme. Because it encodes the differences. Encodes the, and this is important, it encodes the difference of the signal. It encodes the difference of the signal samples, correct. Further, if you look at delta modulation, each bit or each sample is represented only using a symbol. Each sample is represented only using a simple. Each sample is encoded or quantized, encoded using a single bit. Hence, this is a very efficient scheme. Hence, it results in a very low bit rate. Hence, it is very well efficient. Efficient in the sense that it results in a low bit rate, results in a very low bit rate. It results in a very low bit rate. And can also be used for compression. Can also be used for compression. Okay. Now, we also saw, right, we also saw the procedure for delta modulation, okay, and the reconstruction for delta modulation, which is carried out at the receiver, can be done as follows. So, we have MQN minus 1, remember MQN, right, which is approximation, MQN minus 1, which is approximation to the signal at time instant n. So, I have MQN minus 1, remember, I have MQN minus 1, which is the quantized approximation to the signal at time instant n minus 1. This is the quantized approximation to the signal at time instant n. This plus EQN, remember EQN, right, EQN is delta times sine of En. This is the, remember, this is equal to delta times sine of En, which is basically the quantized error, correct, which is basically quantized error, which is basically quantized error at at time n. Therefore, your mqn minus 1 plus eqn equals mqn, where mqn is a reconstructed signal at time instant n. Okay, mqn is a reconstructed signal, mqn is a reconstructed signal at time. So, you have mqn and that is a very simple reconstruction equation. This is our signal reconstruction equation. This is our equation for signal reconstruction. Okay, let us note that this is our equation for signal reconstruction at the receiver, okay, or wherever we are doing reconstruction. Okay, so this is our equation this is our equation for signal reconstruction. Okay. So, now let us see how it works. Whenever we are doing signal reconstruction, we have time, okay, and it is very simple, as we have seen already. The procedure itself is very simple. We have mqn minus 1, correct, we have mqn minus 1. Okay. So, the reconstruction at n minus 1, this is mqn minus 1. At this point we have time instant n. So, this is time instant n minus 1, time instant n. So, mqn minus 1, this is the approximation, this is reconstruction at n minus 1 as well as the approximation at, so mqn minus 1 is a reconstruction. So, note that mqn minus 1 is a quantized approximation to signal at time instant n as well as reconstruction at this is also the reconstruction of the signal at time n minus 1, that is a reconstructed level of the signal at time instant n minus 1 itself is an approximation to the signal at time instant n. Alright. So, naturally to this I add the quantized error. So, this is your mqn minus 1, to this you add eqn, which is either, remember this is either plus delta or minus delta, eqn which is the quantized approximation to the error in delta modulation, this is equal to plus delta or minus delta. So, this is also something that can be noted, this is either plus delta. So, eqn equals either plus delta or minus delta. Okay. This is the quantized error at time n, which is either plus delta or minus delta. So, eqn, and that gives you finally the quantized. So, that is your mqn, that is the quantized approximation of the signal at time instant n. And similarly, one can again at n plus 1 you can add eqn plus 1 to obtain mqn plus 1, and that is how we get the staircase approximation to the signal. So, we get a staircase approximation to the original signal. So, we get a, so this is your staircase approximation to the, as we have said, a delta modulation gives a, this is a staircase approximation of your original signal. Further, now observe that this staircase approximation is coarse. So, I pass this to a low pass filter, this is, so because this is has sharp edges, I pass it through a low pass filter LPF, appropriately chosen bandwidth, and what that will do, that gives me a smoothened version of the signal. So, the LPF, so this after passing through the LPF I get a, after passing LPF one obtains a smoothened version of the signal. One obtains a smoothened after passing through a low pass filter, one basically obtains a smoothened version of the signal, because remember in a staircase approximation we have sharp rises, all right, we have sharp corners, sharp rises and sharp falls, all right. So that gives rise to high frequency components. So naturally to remove those things, pass it through a low pass filter of suitably chosen bandwidth, right. Naturally that has to be the bandwidth of the message signal, all right. Once you pass it through a low pass filter, then obviously you are going to get a smoothened version of the signal. Okay, that is a smoothened version of the reconstructed signal. Okay, so now let us look at a schematic diagram for the delta modulator. So I want to look at a schematic diagram of schematic diagram of delta modulation. Now, if you look at a schematic diagram of delta modulation, you are going to have sample Mn, okay, this is the sample at time instant n, okay, this is your sample Mn, okay. Now from this sample, remember you are subtracting, remember you are encoding the differences, so you are subtracting mq of n minus 1. So from this sample you are subtracting mq of n minus 1. This is passed through your 1-bit quantizer, that is delta times sine of E of n. So this is passed through a 1-bit. So this Mn minus Mq of n minus 1, this is your E of the unquantized error, E of n. So this is the unquantized error. This is your unquantized error E of n. You pass it through the 1-bit quantizer and then you get EQ of n. You get EQ of n. Once you pass it through 1-bit quantizer, you get EQ of n. Okay. Now this EQ of n, remember, this is equal to EQ of n equals plus or minus delta. So this has to be encoded, okay, to obtain the information stream. Remember we said encoding is the process where you are mapping this to plus delta, for instance, let us say to 0, or for instance you can map plus delta to let us say 0 and minus delta to 1. Okay. So you get an information bit stream of zeros and ones. Okay. So that is the job of the encoder. So you get an encoded bit stream of zeros and ones. So this is basically your encoded bit stream of zeros and ones. Okay. So let us note that down. So encoder, this is your encoder, this yields your encoded bit stream of bit stream of 0, 1, encoded bit streams of zeros and ones. And of course, now this EQN, we are not done with EQN. Remember EQN has to be added, EQN has, now we have EQN, alright. So we have EQN has to be added to MQN minus 1 to give MQN. So we have EQN So, we have EQN, we have MQN minus 1, we have EQN, that gives us MQ of n. This gives us MQ of n. Now, this MQ of n you pass it through a delay. Okay. So, you delay it by one sample, this is your delay, that gives us. So, MQN, pass it through a delay of one sample, that gives rise to. So, the Z inverse basically is a Z transform, some of you might be familiar with it. This Z inverse means it is a delay of one sample. So, MQN is delayed, pass through the Z inverse module, or let you delay it by one sample, you get MQN minus 1. Now, MQN minus 1 is subtracted from MQM to get E of n, that is unquantized error. At the same time, NQN minus 1 is added to EQN to get MQN. Alright. Now, MQN is basically going to be the reconstruction at time instant n. It is also, remember, it is also the approximation for the closest approximation for the signal at time instant, because MQN is subtracted from M of n plus 1. Alright. So, M of n plus 1 minus MQ of n, that gives us E of n plus 1 and so on. Okay. And of course, the encoder takes in EQ of n, that is the plus or minus deltas, right. The 1 bit quantizer produces plus or minus deltas, the encoder takes this, right, plus or minus deltas and maps them into information bit stream, that is ones and zeros. These can either be stored, alright, in memory, or these can be converted into an appropriate digital modulation mapped to again a digital modulation constellation, alright, digitally modulated, right, and then transmitted over the channel. So, these ones can be stored or digitally modulated and transmitted over a digital communication channel. So, that is how we are getting from a continuous signal, that is first sampling it, quantizing it, converting into a bit stream, digitally modulating it and transmitting it over the channel. Okay. So, this encoded bit of zeros and ones, so this is the encoded bit of zeros and ones. So, this can be either stored in memory, in an appropriate memory, or this can also be digitally modulated and transmitted over a communication channel. This can be digitally modulated and transmitted over a communication channel. So, this is basically your schematic of a delta modulator, alright, which basically, as we said, is very efficient because it basically quantizes the differences and quantizes them and represents them using only a single bit. So, that is basically providing a single bit per every input sample. Okay. So, that is basically the idea, and that is basically also the advantage of delta modulation. Now, let us look at the schematic for reconstruction. Let us look at the schematic for reconstruction. The schematic for reconstruction, as we have seen yesterday, that is very simple, or as we have seen today, that is in this module, is very simple. So, we have the decoder, we have the input bits. Okay. So, you have the bits. So, this is your input bit stream. We have the input bit stream. Okay. So, this is your, that is the encoded input bit stream. Naturally, that has to be passed through a decoder. The encoded bit stream has to be passed through a decoder. This is then, this is what we get EQ of n, the bit stream, you can get the quantized errors. EQ of n is nothing but the quantized errors. To this you add, it is very simple, you add mq of n minus 1, the reconstruction at time instant n minus 1, mq of n minus 1, you add nq of n minus 1, all right, you add mq of n minus 1, now that gives you mq of n. Okay, that gives you mq of n, that is a reconstructed signal at time instant n. Okay. Now, that is passed through your low pass filter to obtain the smooth end signal. At the same time, we have mq of n itself forms the closest approximation at time instant n plus 1. So, we have this is mq of n, again remember Z inverse is simply a single sample delay. Okay. Z inverse, whenever we have Z inverse, of course, some of you might be familiar from the Z transform notation, this is a single sample delay. Okay. And therefore, you get mqn and this is the your reconstructed signal. Okay. This is your reconstructed signal. So, this is basically the schematic, which is a very simple schematic. All you are taking is basically you have the reconstructed signal, it is a recursive process, right. You have the reconstructed signal at 10 n minus 1 mq n minus 1, that forms an approximation at time instant n. So, mq n minus 1 plus the quantized error eq n, that gives mq n, which is the reconstructed signal at time instant n. So, now you have the staircase approximation of the signal, which has sharp edges, pass it through a low pass filter to get a smoothened version of the signal. All right, it is a very simple scheme. All right. So, you have delta modulation for differential encoding, right, basically encodes the differences using a single bit, and the optimal the appropriate reconstruction. So, let us now look at conditions of delta modulation the distortions, various distortions that can occur in delta modulation. Okay. So, we want to look at delta modulation or the distortions of delta modulations or distortions in delta modulation. And the distortion in delta modulation can occur as follows. For instance, if the step size is too small, step size delta is too small, and the signal mt, that is the signal to be sampled, rises very fast or it falls very fast, all right, then the staircase approximation can fall short of the signal. Okay. So, let us look at the first distortion. Too small step size delta occurs if that is we have a too small step size delta is too small. This leads to the fact that if signal rises or falls very rapidly, in comparison to the the signal rises or falls very rapidly in comparison to the staircase approximation, we are going to have a problem. For example, For example, if we have a signal, the signal is rising very rapidly, but my staircase approximation, because we have a small delta, correct, the staircase approximation is never able to catch up, is not able to catch, is constantly fall. So, delta, of course, if delta is large, then at some point, for instance, if my delta, on the other hand, if this same signal, if I have a large delta, for instance like this, delta is sufficiently large, right, then my staircase approximation will be able to catch up at some point. So, this is basically your large delta, and this is basically your small delta. And in this scenario, what is happening, staircase approximation is falling short of the signal, right. The staircase approximation falls short the staircase approximation falls short of the signal. Okay. So, this is the problem with small. Similarly, if the signal is falling rapidly, on the other hand, if the signal is falling rapidly, so here signal is rising rapidly. Okay. Now, this is the difference. Signal is rising very rapidly, okay, and here on the other hand, signal is falling very rapidly, and again, once again because of the small step size, correct, once again because of the the signal is not able to. So, if we have a delta approximation which is basically here at this point, the signal is let us write it this way, the signal is falling very rapidly, and once again the delta approximation is not able because of the small delta is not able to catch up with the signal, so on. So, my signal is falling very rapidly and delta approximation, the staircase approximation is not staircase approximation is not able to catch up with the signal, let us put it that way. So, in both scenarios, when the signal is basically rising very rapidly or falling very rapidly, or in other sense, if the slope of the signal is too high, right, when the slope of the signal is too high such that the staircase approximation because of the small or limited delta size is not able to match, right, is not able to match the rapid increase or rapid decrease in the signal, that leads to slope overload distortion. That is, there is a very high slope which is overloading your delta modulator. So, that leads to slope overload distortion. So, very high, very rapid rise or fall in the signal. Very rapid rise or fall of signal implies very high slope that overloads the delta modulator, leads to this leads to slope this is termed as slope overload distortion. As a result of slope overload distortion, there is a high error between the staircase approximation and the actual quantized signal. So, this results in a high error original signal empty and reconstructed signal from the delta modulation. Reconstructed signal from delta modulation. Okay, reconstructed signal, it leads to a high error, correct, it leads to a very high error between the original signal and the signal reconstructed from the delta modulation. On the other hand, right, when the step size is too large, now let us see what is the problem. So, this slope overload distortion, remember slope overload distortion, this arises from ultimately from too small step size. Now, when step size is too large, when we have too large step size, then we have the other problem. If the signal is relatively flat, okay, signal is relatively flat, signal is relatively flat, signal is relatively flat, then we have a, so if the step size is very large, right, and the signal is relatively flat, we have a large approximation error. Okay, so, this is large delta. So, this causes large delta. So, the staircase approximation, the error between the staircase approximation and the signal is relatively large in comparison to, let us say we have a small value of delta, let us say we have a smaller value of delta, which I am drawing with a different color over here, correct. You can see that if you have a smaller value of delta, smaller value of delta leads to, this leads to smaller error. Leads to smaller error between empty and the reconstructed signal, that is our staircase approximation. Smaller error between the staircase approximation. So, while a large delta might be suitable to avoid slope overload distortion, the larger the delta, that leads to a larger error when the signal is relatively flat, because when the signal is relatively flat we desire a smaller value of delta. Therefore, this distortion which is arising from the from a large value of delta when the signal is relatively flat, this is termed as granular noise. Okay. So, and naturally this is termed as granular noise. All right, and granular noise is arising from a large value of delta when the, or large value of step size delta when the signal is relatively flat. Or when the signal is relatively flat implies that the slope is low, relatively flat, which implies low slope, and that is causing this granular noise. Okay. So, we have, and these are basically you can see sort of the counterparts of counterparts. So, we have a large small delta. If you have a small delta, then the staircase approximation is not able to keep up with the signal when it is rising or falling rapidly, that leads to slope overload distortion. Large delta, if you have large delta, the approximation is very coarse, especially when the signal is not rising or falling rapidly, that leads to granular noise. So, we have two different kinds of distortions in delta modulation. In delta modulation, we have two different kinds of distortions. Let me just summarize this. When we have a large delta or when we have small delta and signal is rising or falling rapidly, that implies we have slope overload distortion. When we have a large delta, when the signal is relatively flat, that leads to granular noise. So, these are the two different kinds of distortion. Now, if you have a large delta, of course, that also implies a wider dynamic range you can capture, because the delta, the step sizes are large, you can span a larger range, right. So, which means you can capture a larger dynamic range very fast, alright. But however, the slope overload distortion is also huge. Okay. Now, if the delta is small, then the approximation is very fine, right, the approximation is very fine. So, the noise is low when the signal is varying slowly, but if the signal is varying very fast, then the noise is very high. So, that alright. So, when you have a large delta, obviously when the signal is varying very fast, you can capture it, correct, but if the signal is varying very slowly, then it leads to granular noise, alright. So, these are the two. So, this is, so one has to choose this step size delta intelligently. Okay. So, the step size delta has to be chosen intelligently. So, there is a trade off of small delta versus large. So, the step size delta must be chosen with care. I will say step size delta must be chosen optimally. Must be chosen carefully. Okay, it must be chosen carefully to avoid both slope overload distortion and granular noise. Now, one particular scheme which adaptively chooses this delta size depending on the signal is adaptive modulation. Adaptive delta modulation adapts this delta size optimally so as to match the signal conditions. All right, we are not going to look into this. So, to match nature of signal one can choose adaptive delta modulation. In adaptive delta modulation, what happens is the step size delta is adaptively changed. In this, the step size delta is changed adaptively, or it is adapted. Let me, that is a better word, it is adapted according to the signal to minimize both slope overload distortion and so it is adapted, right, according to the, it is adapted according to the signal to minimize both the slope overload distortion and granular noise, which means basically if the signal is varying very rapidly, is rising or falling very rapidly, then obviously the delta must be made large, all right. On the other hand, if signal is varying relatively slowly, that is relatively flat, all right, slope is low, then the delta size can be made small. Thereby basically you are minimizing both error occurring due to slope overload distortion and also due to the granular noise, all right. So that basically completes in essence delta modulation. As we have seen, if it is a very efficient modulation scheme, it is a differential modulation scheme which quantizes the differences between successive samples, all right, and also it employs a single bit for quantization, which makes it very efficient for both communication as well as compression purposes.